This is your good friend Professor Cleary with my good friend, there he is, on Mardi Gras. Now Marty wants to impress the boss by doing a capability study, and he goes and gets some data, and here's what his data looks like. It's got a mean of 10 and a standard deviation. So let's start off by drawing a picture of that. Take a look at my little pointer here. Here's my process average. If it's we assume a normal distribution, how would we draw that? Well, if you go to the right, 3 standard deviations, okay, here we go, 1, 2, 3 z values. The standard deviation is 2. I'd go from 10 to 12, 12 to 14, and the upper tail will come down about 16. The lower tail, well, I go from 10 to 8, 8 to 6, and there it is, 6 to 4. So that's a good picture of this data. Well, what about the specs? Well, here's the upper spec. Boom, it's right there. There's 14. Lower spec. Boom, it's way down here. We can see we're making some bad parts. In this case, it estimates 2.28. Fine. Marty goes off, gets to his book, and he says, I'm going to do a CP value, capability. And he does it. And he does it right, by the way, because a CP is equal to the upper spec minus the lower spec divided by 6 sigma. And there is 14 minus 0 divided by 6 times 2. There it is, 1.17. Of course, Marty's happy. He says, I'm great, because he heard somewhere that a CP, if you're capable of 1 or more, you're in heaven. Well, guess what? Boss says, Marty, I think you should go back to that book, that Practical Tools book. And I now want you to go, because I now want not a CP, I want a CPK, because I've heard that's a better way to reflect capability. So Marty says, fine. He gets the book out, reads a section on what it is, what does it look like, when is it used, and of course he studies this very carefully. He has to know how it's made. And here's Marty's attempt to go do that. And here's the data. Same data as I had before. Okay, the mean is 10, the standard deviation 2. You can see it looks just like before. But now it's different. What's a CPK equal to? It says take this thing called the Z minimum, whatever it is, and divide it by 3. The smallest of the two. In other words, a z minimum, take the smallest z and do that. Well, what are these z values? Well, really what the CPK is doing is saying this. Tell me how many standard deviations the upper spec limit is from the center. Well, you can do this visually in this case, because here I go from 10 to 14, 10 to 12, 12 to 14. How many z values am I to the right? I'm 2 z values. Well, that's fine here because the numbers are easy to see, but we need a formula for that. Well, really a way to calculate that is take the upper spec minus the process average divided by sigma, in this case 14 minus 10 divided by 2. There's the same answer. I'm 2 z values to the right. Fine, that takes care of that z value. What about the other z value? Well, same thing. How many z values is the lower spec from the center? Well, look here. 0 to minus 1, minus 2, minus 3, minus 4. Minus 5. Well, we disregard the sign because down here the z upper spec limit is x double bar minus lower spec limit divided by sigma, and there it is. It's 5. That's saying in English the lower spec limit is 5 z values of 5 standard deviations away from the 2. Okay, high math here. What does it say? Take the smallest, 2 or 5. 2 is the smallest. 2 divided by 3. There it is. Now there's your CPK. In this case, the CPK would equal to 0.67. Now a lot of people get that mixed up. They say, what is that? 67% of the parts are good, or what does that mean? Well, let me show you a way I try to help my students in terms of understanding this. And here's what I do. I created a new situation. I've got the same basic distribution, the mean of 10 and a standard deviation. See it right there? So that doesn't look any different. But I've changed my spec limits. The upper spec limit's 16, the lower 4. Well, what you can see what I've done, I've set it up such that the upper spec limit will come down right at the end of the tail, or 3 z values to the right, and the lower spec limit is going to come right down at the end of the tail, 3 z values to the left. Well, most people would remember from their stat, if I go plus and minus 3 z values, what do I capture? 99.73% of the area under the curve. Or in this case, if I go back to my mechanics, I simply do the same thing. I had the z upper 3, z lower 3, 3 divided by 3, 1. Therefore, my CPK in this case is equal to 1. What does that say in English? I'm producing at least 99.73% good parts. Alright, well, wait a second. What about this word at least? Why did I use that word instead of being definitive? Well, let me give you a second situation that can bring that out very nicely. Here again, I've adjusted the data in this fashion. I still have that same distribution. The mean of 10, standard deviation of 2, so tail comes down at 16, tail comes down at 4. But now my upper spec limit's the same. It's at 16. So therefore, when I do the z upper, again, that's 3 z values to the right. But look at the z lower. What I've done is I've taken that lower spec limit and I've made it 0. And therefore, if you look at it visually, how many z values away is that? 1, 2, 3, 4, 5. Or if you want to do it arithmetically, it would be 10 minus 0 divided by 2, it's 5. And therefore, in essence, I draw it that way. Now again, which of these two are the smallest? This one. All right, this doesn't matter in my calculation. So 3 divided by 3 is equal to 1. Here, well, the point I'm trying to get at is here I again have a CPK of 1. But am I producing 99.73 together good parts? No, I'm producing more than that. On this side it would be the same, but look over here. In essence, it would be minuscule. So you would actually be producing more than 99.73% good parts. So therefore, this statement is very, very good. If you have a CPK of 1 in your head, think about that, is you're producing at least 99.73. You might even be producing more if you had a case like this. Anyway, that's just this month's quality quiz on capability, CPK. Hopefully that gives you a better idea of what a capability index means. Bye now.